a given function. I think we all can remember commercial buildings or structures which failed, causing loss of life and property. Sometimes these failures were due to design flaws, and other times the structures were asked to withstand additional and unforeseen stresses that simply could not be planned for. In this lesson, we will look at how buildings are designed from a structural point of view. We will look at forces and loads which act on the structural components of buildings. We will be taking a close look at beams and columns. In addition, a design problem will be presented which will be solved in the second lesson in this series on structural loads. The primary function of a building structure is to support and transmit the loads and forces to the ground. There are three characteristics which need to be considered. The first is stability, which is needed to maintain shape. The structure is dependent upon balanced forces and being in equilibrium. The second is strength, the ability of the structure to withstand the applied forces. This usually includes a factor of safety. And third is the building's economic value. This includes, but is not limited to, choices which are made about the design, the materials used, the construction costs, the maintenance and energy costs, and the intended function of the structure. The structural elements in the building consist of stringers or beams, girders, columns, footings, and the connections which tie it all together. When a structural engineer is designing a building, there are certain steps that he or she follows. Engineers first need to plan and determine the function that the structure will serve, such as an office building, a school, post office, or hospital. Then they need to create a preliminary structural configuration or layout. They will need to establish the loads to be carried and create an initial sizing of the members needed. Once this is done, then an analysis of the members will be calculated so that these calculations can be evaluated and compared to the preliminary design. Since this is an iterative process, a redesign would be needed. The last step would be to design and detail the final structural components. Various loads act on the structure in conjunction with various other loads. Dead loads are fixed loads and are simply the weight of the materials that compose the structure. Live loads are the weight of anything which is not fixed in place. These could include snow loads, the weight of people and their possessions, and furniture in office spaces. Live loads may be variable during the structure's lifetime. In order to calculate live loads, the engineer must depend on building code specifications. These specifications are based on typical load capacity provided by structures that have withstood the test of time. Minimum values of live loads are dictated by state and local building codes. The live loads that are listed in these codes are generally conservative. A sampling of live loads taken from the AISC Manual of Steel Construction has been compiled for you. Please pause this lesson and use the link provided to obtain a copy for yourself and your students. We will be using many of the values provided later in the second lesson. Dead loads are gravity loads, since gravity acts downward and is always present. The weight of the structure is considered a dead load, as are partitions, girders, beams, stringers, ductwork, lighting fixtures, plumbing, floor covering, just to name a few. Although dead loads are generally known, many of the details in regard to actual material cannot be made until the design is finalized. Dead loads can be treated as uniformly distributed. Dead loads are determined by using the density of the material and converting it to uniform loading condition. We have again created a chart of typical building dead loads taken from the AISC Manual of Steel Construction. Once again, we invite you to pause the lesson to obtain a copy of this chart for your use. Press play when you are ready to resume. Conditions when thinking about loads. In parts of the United States, snow loads are a factor. For example, snow loads for various cities in New York where it snows are shown. If you live in other parts of the country which do not get snow, you might not need to take snow loads into consideration. Wind loading is another design load that has an impact on the design of the structure. Wind loads can vary depending on the location and the height of the structure. This is referred to as the exposure categories in the building codes. For low-rise buildings, the wind load can be transferred through shear walls such as masonry wall in an elevator shaft and the exterior masonry wall or steel bracing in the structural frame. For a tall structure, the wind can force the building to lean sideways. A building designer needs to take these loads into effect. Designers can do this by taking into account the building's dead loads, which help resist the overturning and uplift conditions caused by wind. Typically, a building framed with steel beams and columns will have some type of bracing to handle the wind load conditions. In addition, the slab floor also resists wind loads and shear loads. In some regions of the world, the structural engineer needs to consider earthquake or seismic loads. These loads are based on the location of the structure, the soil type the building site is set upon, and the shape of the building. Engineers need to depend on seismic maps that depict the potential risks for the location of their building. The structural efficiency of a building is measured as the ratio of dead to live load. The building designer always strives to keep this ratio low. The load factors used in structural design provide a factor of safety for the loading conditions imposed on the structure. The load factors are multipliers that increase the loads that are either calculated by the designer or required by building codes. In general, dead loads are multiplied by 1.4, which yields a 40% increase. Live loads are multiplied by 1.7, thus increasing the loading condition by 70%. In order to maintain simplicity, we will not be using factored loads for the CEA problem posed in the second lesson. However, this is important information to share with your students. For all structures, the load path must be traced from top to bottom. Sometimes this is called chasing the load. When following the path, one needs to take into effect the snow or roof load, the load of the occupants of the building and all the equipment placed inside the space, the weight of the structural components themselves, and the ground reaction. The building dead load is the only known load. All other forces will vary in magnitude, duration, and location. The building must be designed for design load possibilities that may never occur. Beams are used by the design engineer in roofs and floors. They may be called joists, stringers, beams, or girders. Sometimes the loads on the beams are concentrated, and other times they are uniform. All beams are designed for shear, moment or bending, and deflection. Beams are sized to safely support the loads a structure will carry with the minimum amount of material to save costs. Deflection of a simple beam is more important than bending. Deflection can cause a ceiling finish such as plaster to crack or a floor finish such as tile to break. Both are undesirable. other concerns. Excessive deflection may cause building vibrations that can lead to load failure when the beam resonates, or excessive deflection may shorten a beam to cause it to slide off its support. However, the major concern when designing a building and thinking about deflection is the ponding of water on roofs. The additional weight of water can cause roof leaks and excessive additional loads. In areas such as the northern part of the country where there are measurable snow accumulations, when the snow melts and the roof drains are clogged, ponding and deflections have caused more than one roof to fail. Yet another reason that deflection is important to consider is simply a psychological one. When there is a deflection which is able to be detected by people, they think the structure is unsafe. Therefore, it is up to the building's designer to determine how much deflection is allowed or desirable. Deflection can be limited using many formulas. Two of the most common ones are L divided by 240 and L divided by 360, where L equals the length of the span in inches. L divided by 240 is used when there's no plaster or drywall on the underside of the support beam. L divided by 360 is used when there is plaster, drywall, and this is the preferred method or limit. The method of support is an important one. A conservative approach for calculating loads is to assume that the beam or girder is a simple span. Supports are determined by their method of attachment at the ends or bearing locations of the beam. These can be pin, roller, or fixed types of supports. Columns carry primary axial loads and therefore are designed for compression. Additional loads from snow, wind, or other horizontal forces can cause bending in the columns. Therefore, columns need to be designed for axial load and bending. In the second lesson in this series, we will be following the design steps to analyze the members of a steel-framed retail building with concrete floors and a flat roof. In preparation for this, please pause the lesson and obtain the Revit file used to model the structure. Take some time to look at the file before participating in the second lesson. This design was created for illustrative purposes only using R simulation software. Not all the steel framing members are accurately noted and resized for the final design. Remember that the visibility of walls, the roof, and the floor slab can be changed to see the entire framing plan by turning on and off the visibility under the Properties tab. For example, in order to get a clearer view of the girder, the internal support beams, the columns, and the footings, the visibility has been turned off on the ground floor slab, the second floor slab, the roof framing, and the roof deck. Please try this with the Revit file you just saved. Let's go back to our earlier discussion about the steps needed in structural design. Planning the structure function for its intended purpose and optimizing the design in terms of cost, material type and weight, and the construction time are all part of the planning stage. This stage is done both by the architect and the structural engineer. The preliminary structural configuration was based on the layout required. The loads of the structure are determined through the use of construction standards and building codes for the site's location. The preliminary sizing of the members involved estimating the size of the structural members and the weight to be carried by each structural element. Now, we need to analyze the structure by calculating the required loads and sizing the structural members properly. Once that step is completed, we can compare the design to the preliminary assumptions we made about weight and other assumptions which were made during the early stages. We will then be able to redefine the loads and recalculate and resize structural members. The last step would be to design the connections for the structural members